So, ladies and gentlemen, it got quiet all of a sudden. First and foremost, because lately I've been forgetting because I'm old and forgetful, in the event that you have an electronic device on you, if you would be so kind as to turn it off presently, I would greatly appreciate it. Also, in the event that you did not basically sign one of these sheets, if you could at the very least put your name and the city where you live on there, I would greatly appreciate that as well. If you would like to put your birthday down, that's an added bonus. I know that the guys listed the sponsors, but thanks to the guys because they help out. And I guess one of the other sponsors that hasn't been listed lately is you. As most of you know, Oregon Resources Corporation, with the current global economy, is not doing as well. So we're hoping to get them back as a significant sponsor in the coming year or so. But your contributions already this year have amassed to over $1,400. So a bunch of people that I have run into of late have mentioned the quality of the speakers this year and in the past, and the hope that it continues into the future, and it definitely will. But your generosity is also helping with things like that. This evening, Dr. Brandon Dugan is here from Rice University, and one of the reasons he's here is the Consortium for Ocean Leadership. And as an institution, we've been really very fortunate over the past decade to host at least 6 speakers from their Distinguished Lectures series. And so that has been a major contribution, and basically over the course of the last roughly 36 hours, Brandon did a session with some students. He, as well as 3 other individuals from Washington, D.C., California, and Texas, have been in town helping teach some of our local teachers from both the general area as well as far away as Eugene, Cresswell area as well. So it's been a kind of a whirlwind day and a half, I think, out on the coast for Brandon and this other group, but it's been a real pleasure to have them in our community. So without much further ado, Brandon Dugan, as I mentioned, comes to us as a Consortium for Ocean Leadership Distinguished Speaker from Rice University. He got his master's in Minnesota and his PhD at Penn State, and so is going to speak to us tonight about submarine landslides. Brandon?
Thank you very much, Ron, for that introduction. I'd like to thank the Consortium for Ocean Leadership, the college, and the community for inviting me here today and supporting this visit. I've had a great visit, got to see a lot of local geology, got to meet a lot of people, and today, hopefully I can convey some information to you, continuing on some of the other geology lecture series talks that you've had. I know there's been some geology lecture series talks on tsunami, definitely an area of interest for this community. There have also been some people talking about earthquakes, also an area of interest for here. But today we're going to focus on something a little bit different. We're going to focus on submarine landslides, and sort of the idea here is you can have large failures, just like landslides on hill slopes, that happen in the deep ocean. And depending on how they happen, how quickly they happen, and where they happen, they can be inconsequential, just moving around a lot of sediment in the ocean, generating small ripples in the ocean, or they can be large and catastrophic and generate deadly tsunami that can kill thousands of people. But what we're going to focus on today is a little bit of an education, a little bit of roadmap about how and when these submarine landslides occur. As a backdrop to this, the ocean drilling program has provided almost all of the data and supporting information that I'm going to use in this talk. And just to give you a range of ideas, this is a map of the world. All the blue is our oceans, and each one of those dots on the map is somewhere that scientific ocean drilling has gone out to attack some problem, ranging from how deep beneath the Earth's surface life exists, what pressures and temperatures it exists, looking offshore Japan over here, how do we get, oops, I thought I turned my wireless off, excuse me, how embarrassing, it is off, oh well. How big earthquakes happen, we can look at Japan, or we can look at Sumatra, which most of you are probably familiar with over the last 9 years. We can also look at things like how the uplift of the Himalayas has affected global climate by looking at climate signatures. So there's a whole range of problems that we can solve, and today we're just going to focus in on one very specific example of how we can collect data to understand large submarine landslides. So I like to start with the end. If you want to remember anything from this talk today, there are really three things that we're going to try and drive home. One is that overpressure, and here we're thinking about the pressure of the water down deep in the ocean. So everybody's jumped into a swimming pool and swam down to the deep end and your ears start to hurt. Imagine if when you swam down 10 meters or 30 feet down beneath the ocean, rather than that normal pressure, you had twice as much pressure or three times as much pressure. That's what we're looking at, pressures in excess of what you would normally exceed. It's difficult to generate these large failures by overpressure alone, and I'll show you some examples of why we think that is the case. And then we'll wrap up the talk with showing how much pressure starts out in the system may impact what the failure looks like and how far it moves. And really that's the tsunami-genic potential. If it's a big failure and it moves really, really far, it can generate a large landslide. If it's a big failure but it moves slowly, it doesn't really do much damage. And those are sort of the things that we're trying to tackle now, and I'll come to that at the end of the presentation. But why are we studying this problem goes back to, I don't know how many people were here for Brian Atwater's talk a while ago when he visited, is looking at onshore deposits and then linking them to offshore problems. So there's this problem known as the Gus Slide, which is a large submarine landslide. Here's a topographic map of our wonderful state. We're sitting here. I had to learn that before I came to visit. Where was Coos Bay? Where is Coos Bay? But now I know. And for a frame of reference, it's about 500 kilometers from west to east across this state. So just to keep that in mind for a minute. The Gus Slide was actually discovered by looking at deposits, tsunami deposits, 30 feet above modern ocean surface levels onshore of the United Kingdom and onshore Iceland. They saw these oceanic debris that was washed up on top of cliffs. And people started looking at this and they said, well, how do I get this modern ocean environment 30 feet above the sea? And I can do it if I have a huge wave that cascades across the ocean and push sediment up on top of these cliffs. And so we went out and started looking at the ocean, and we see this feature. It's a large submarine landslide outlined here. Here's a scale bar again, 500 kilometers. So that's the width of Oregon. And there's a landslide region up here, Gus Slide. Started up here, and that slide moved over 500 kilometers, probably on the time scale of a few hours. So imagine taking a few hundred cubic kilometers of material from the eastern side of the state and moving it in a few hours all the way to the western side of the state beneath the ocean. As you're doing that, you create a wave on the ocean surface, and that wave gets propagated out, generating a tsunami. And they said, okay, well, we can take that mass, and we can move it really quickly, and we can run a bunch of computer simulations to see how big of a tsunami you get. And so some other colleagues did that, and this is just a computer simulation of what the tsunami looks like for a certain slide velocity and slide size. And they showed that you can actually get waves running up on Iceland that are 10, 20 meters high. You can get waves up in the United Kingdom that are 10 and 20 meters high. So empirically, people said this was a large landslide, and it happened at a certain speed and certain velocity, and that generated these waves and washed a bunch of the seafloor up onto these cliffs in the United Kingdom. So that's one example that sort of motivated this research. Another example is offshore Africa, and we're going to look at the Sahara Slide. Here's our same reference, 500 kilometers, just to give you a scale. Now we're looking at the west coast of Africa. So here's the northwestern corner of Africa, the Canary Islands up here, and a submarine landslide or debris flow sort of used interchangeably just south of the Canary Islands. If we zoom in on this map, here's 100 kilometers, so it's about 500 kilometers from here to here. Similar type geometry to the Gus Slide. We have the top of the slide, and it ran down the slope about 500 or 600 kilometers. Again, over presumably a few hours of time period, we moved tons of sediment from up here to down here. And we've looked at this slide in a little more detail, and we went down and we actually measured how steep the ocean floor is down there. And so here's a map of the profile of the seafloor right here to try and better understand this problem. so 600 kilometers difference from here all the way up to here, and the depth of the ocean floor with a lot of vertical exaggeration. So what we've done is we've annotated this figure, and the steepest portion of this slope is 3 degrees. So something like this, for those of you who can see my arm angling out like that. The rest of this slide moved across a surface that is effectively horizontal, less than 1 degree slope. So again, now you've got to think about moving that same amount of mass, tons and tons of sediment, 600 kilometers in 2 hours along a flat surface. So that made us ask a whole different series of questions. Why do these low-angle slopes fail? For anyone who's ever built a sandcastle, you know, if you build up the sand too high, it'll just fall because it gets too steep. 3 degrees is not too steep. All of these sediments should be stable and not falling. And also the question of why are some of these failures so large and thus have large tsunamigenic potential. So I went back to the literature and started reading from the 1950s, a bunch of famous geologists, and they came up with my favorite experiment ever, which is the beer can experiment. And probably on a Friday afternoon, after work, they built a little plank like this, and they emptied a beer can. I'll leave it to your imagination to figure out how that beer can was emptied. And they set that beer can upside down on this plank, and it was in a stable condition. So they just put the beer can on this plank, and they set it there. Maybe it's at a slope of 3 degrees. And they started asking the question, how can we make this can slide down the slope? Does anybody have any ideas how we can make the can slide down the slope? Lift the can up and put oil on it. So one thing you can do is you can add weight to the can, which actually increases the downslope gravity component. You can also change the frictional properties by putting oil between it and make it a slicker surface. Those are 2 things that you can do. Perfectly good. Any other ideas? Vibration, right? I can go and I can shake that and it'll start sliding down the slope. And there's actually one other thing that this paper came up with, and I'm not going to tell you unless anybody knows the answer. Nobody else knows? All right. So we're going to try and apply the same principle to oceanic landslides, where I can't go down and oil the system, but that would work. And I also can't change the weight because the sediment has a certain amount of mass, so I can't change that. I can shake it. We'll come back to that later. I can add more mass. So I did this at work, and I was at work, and it was a Thursday afternoon, so we used Coke Zero instead, I guess. And I set up my own little experiment because I wanted to test that the people in the 1950s were actually thinking and not drinking too much. And so I put a can up there, and I'm going to put a second can up there in a second. I'll come in on the right side. Oops. See if it's playing. There we go. It's coming in now. So I'm going to put another can, identical Coke Zero can, just on the other side of that, same glass plank. And you're going to see that this second can slides instantly down the plank. And for reproducibility, I take the can away, and I put it back on the plank, and it's going to slide a little bit more slowly this time, and then it's going to stop. So I'm not shaking it. I didn't put any oil in there. The cans have the same mass. Does anybody want to take a guess at why it's sliding? Exactly. So what I've done is I've added pressure to the system, and that's effectively the key points. We've added pressure to the system to make the can have actually lower resistance to friction. And what I did is, I didn't tell you, is this can, before I put it on the glass, was sitting off in a freezer, and it was very, very cold. And when I put the can on top of the glass, the air inside that can starts to warm up. What happens when the air warms up? It expands. That's pressure. It's going to increase the pressure in the can because it can't go anywhere, and then actually pushes up on the can and lets it slide down the plank. So if I can generate pressure on a slope, I can actually make things fail. So we have a solution. The question is whether or not it's physically reasonable or not. Can I generate enough pressure in the subsurface to get something to slide down? So this led to a proposal that we originally submitted in 1999 and drilled in 2005 to look at some landslides in the Gulf of Mexico. So my home is just up to the west of this bay over here in Houston, Texas. This is the Bird's Foot Delta of the Mississippi River, and we're about 150 kilometers straight south of the mouth of the Mississippi River today in a region called the Ursa region, just on the flank of a big canyon that was carved during a sea level low stand before by the Mississippi River. And what we did is we went zooming in on this area here, so now we're looking at a much smaller scale, 12 kilometers across here. We drilled 3 sites from west to east where we thought there were submarine landslides. We wanted to go in and characterize them. What are their properties? What do they look like? What is their distribution? And then we wanted to understand how they may have formed. So we're going to go through that process today. What did we drill? What did we learn? And could we generate failures in this environment or large landslides? So what we're going to do is zoom in and look at what we call the remote sensing data for this region before we first drilled. And these are what we call seismic cross-sections. So here's some scale bars. Each one of these, scale bar is a half a mile across to give you an idea of scale. And each one of these sections is about 300 meters tall from top to bottom. And these are seismic images. It's the same thing that they use, almost the same technology, to take an ultrasound of a baby. They send energy into the system. They look at energy that's reflected back, and we get a picture of something that we can't see looking at reflections. And we see some very distinct characteristics here. This is the seafloor right here. So above here, this is just all seawater. We've got about 1 kilometer of water on top of us. And we see that in the shallow section, we have nice layered systems. There's a lot of vertical exaggeration here. So this slope here is about 1 degree or something like that, if you want to think about it in terms of scale. And everything's relatively continuous across until we get down to this deeper interval. We start to see that we lose all of that consistency, and everything's all jumbled up, like maybe it's deformed and mobilized or remobilized after it was originally deposited. And then we come back down into continuous reflections again, and that's on the west side. If we move over to the east side, or the center side, we again see nice continuous reflections in the shallow section, and then we get down to this disturbed section, but it looks different than the disturbed section over here. Here I can actually trace some of those original reflections that were probably continuous like this, but they look like they've actually been block rotated across, like maybe they failed like dominoes and toppled over a little bit, creating nice discrete fracture planes. So we've got 2 inferences of landslides that have very different shapes and morphologies, and maybe that tells us something about how they formed. We move farthest to the east. Again, we see a similar type of section, layered sediments, some disturbance, layered sediments, and some disturbance. So we propose to drill 3 transects, 1324, 1323, and 1322, to go in and make discrete measurements. Are these really landslides? What are their properties? What is their composition? And then eventually we could solve how they occurred. So we're going to add together a whole bunch of information, and I'm going to give you a summary of the type of information we look at, and then we'll look at each site individually and summarize what we know about the slides today. And then we'll try and say, what do we know about the slides in the past? So this is just an extraction of what I've showed you before. The nice horizontal layering here, and then we get down into this zone where everything is jumbled up and remobilized, or at least that's our interpretation. We run a bunch of other tools down the hole that measure things like resistivity. We send a current into the rocks. We get a current back. We look at the voltage drop and how much resistance there is. And we can measure the resistivity in that formation, how it changes. And we actually see when we get down to this jumbled zone, we get a big change in the resistivity. And that actually tells us that the sediments have changed their structure. They're now behaving differently. And then when we get down deeper, things become more similar again to what was above. So we know that there's some sort of difference going on there, but we haven't looked at these rocks. We've just remotely tried to characterize them. We can also take pictures of the well that we're drilling, looking around in the borehole. And you see some of these same features. Now we're going to look at a very different scale. This is only 6 meters tall instead of 240 meters tall here. And you see that they start out with some nice horizontal layers here. We have some nice horizontal layers down here. And then you see this discordant layer, which is actually a layer that was originally horizontal and has been folded back on itself again telling us that there's been some remobilization or migration of that sediment after it was deposited. So now we're seeing things at sort of the 3-foot scale rather than the 100-foot scale. And then we can take actual cores and go in and look at them. And now we're looking at another completely different scale, 40 centimeters here. And we can actually see centimeter scale folds and some small faults. It may not show up the best in the picture, so we've done a line drawing of some of these layers. We see offset and distinct horizons, and we see small scale folds where a layer that was originally horizontal has been tilted vertically and then distorted. And one way to do that is to slide down a slope and become remobilized. So we're fairly confident that this is the signature of a submarine landslide. We want to understand all these properties to see how the pressures in these systems behave and how they may or may not fail. So we'll just walk through the information at each one of these sites. 1324, farthest to the west. There's our reference seismic section. We're going to look at 300 meters of data. We're going to look at the same logs for each site. The first is the gamma ray log, which is actually measuring how radioactive the sediments are, and it tells us what it is made out of compositionally. And the key thing here is we see that all these numbers for the gamma ray are higher than about 75, upwards of about 90, and that tells us that it's clay, and we can go in and do all kinds of other measurements. But to put a picture in your mind, this entire section is dark gray clay that is just like the clay you would buy at a modeling store. That's about the consistency of it, to think about what's going on down there. It's malleable by your hands, but it's got some strength. We look at the resistivity, which I already showed to you, and here we see an increase through this section, then it increases at a different rate, and then it decreases down, and we see that that ties up with this discordant section, which we've interpreted as the landslide. And we also see that how dense the sediments are. The sediments come down, they increase in density as they get buried deeper and deeper, and we'll talk about that in a little bit. And then in the landslide, they become more dense, and then after you get out of that landslide, we have a decrease in density. So we see lots of changes in their physical properties, and we also make measurements of strength because we want to know how hard it is to break these sediments for failure. So we can sort of summarize what we see here. We see decreased coherency, that's just the noise that we see over here. We see lower porosity, smaller pores in the rocks, and that relates to increased resistivity and density in our failures. And here we're looking at one failure that's about 50 meters thick. So if you think about how big that failure is, we're talking 160 feet thick of something that's been mobilized and moved down the slope. Now if we move to the center site where we saw that more of domino block rotation, we can go and we can look at the lithology. And again, it's the same dark gray modeling clay type consistency. And here's that resistivity picture that I already showed you, but we pick up a different one. There's a spike in resistivity here. That ties to that discoherent unit there. There's a spike in the resistivity. There's actually 3 spikes here, adding up to 100 meters. So now we're looking at 328 feet thick of failure that was mobilized down a slope. And we also see increased density throughout that entire slide, which means that as it's sliding, it's compacting, it's pushing itself together, it's getting smaller and smaller. And we see different scales of failure here. 10 meters thick at the top, and then adding them up, 3 back-to-back-to-back failures that add up to be something on the order of 100 meters thick. And we move to the farthest site on our east, 1322, and this was one where I'll admit we were wrong from the start, and that's part of science. You're wrong, and you learn something when you do it. We see nice layered reflections here. Here's our original discordant zone, and then we come back into some layered reflections and some discordant zones. And we were pretty sure this was a landslide, and we thought that this was a landslide down here, but we thought everything else was pretty stable and pretty safe. Again, we've got this gray modeling clay type consistency. When we look at our resistivity signature, we pick up a resistivity signature that shows a little bit in the seismic. A nice resistivity signature here that ties with the seismic. And then down here, we see all these little alternating back and forth, peaks and valleys, and they tie to actually very thin failures that are stacked on top of each other. And that's actually recorded as planar reflections, which means that this thing was failing basically as fast as it was being formed, or at least that was our interpretation. And we see the same thing with the density, and again, we've measured the strength here of these sediments, and we'll come back to the strength a little bit later when we talk about it. So here again, we're seeing decreased porosity in failures, we're seeing increased resistivity and density in the failures, and we're seeing much thinner stacked units, sort of 5 to 10 meters, up to a thick unit, maybe almost 50 meters thick, but we don't see the same seismic signature. So even though the rocks are all the same, they're all clay, and they're all the same age, we're seeing very different failure properties, and can we explain or understand that? And that was our next task. So we put together a cartoon of what this region looked like. So we added up all the drilling information that we had, and we combined it with the seismic image, and we said, well, let's just simplify this system down and see if we can understand what's going on. And so to the west, this is Site 1324, and to the east is 1322, and Site 1323 goes through here, and this transect's about 12 kilometers long, and it's about 800 meters thick at its thickest point. And we have 3 type lithologies when you go into the details of it. Down in the deepest part of the section, we have a lot of sand, and this is like nice, high-quality beach sand, unconsolidated, something you'd see if you went to the coast today or on the dunes that you have here. And that's overlain by different types of what we call channel levee deposits, which are basically mud-rich systems with a little bit of sand. And then the very top section is all mud. And each one of these units that is labeled MTCs is where we've identified different types of failure units. And so we said, well, here's a simple cartoon. Can we make this even simpler to try and understand a little bit more about how this system evolved and how these failures occurred? And so here's our simple system for those of you who love math. For those of you who love math, you can look at this slide for the next 2 minutes. For those of you who don't, this is math with words. We're going to try and look at how the pressure changes in that system. Think back to our beer can experiment. We want to look at, can we generate more pressure in that can as a function of how fluids, water in this case, is flowing into and out of the system. If I flow more water into the system than goes out, the pressure has to go up. If I flow more water out than comes in, the pressure has to go down. And also, any extra pressure sources that I have in the system, in time, the system's being buried deeper and deeper, which means I'm squeezing those rocks down. As I'm squeezing them, that's applying pressure. If I squeeze a water balloon too fast, what happens? Pops, right? Because I've put a bunch of pressure in that system. It wants to get out. I'm also, as I'm burying it down deeper and deeper, it's getting warmer, and that water's expanding. So we're just going to look at how the pressure changes with time due to fluid flow in and out of the system, and how we're squeezing and heating the system. That's all we're really going to solve with a lot of fancy mathematics. And what's key here is the geometry of that system. So if we were to do this in a very simple world with a simple sand at the bottom, so what I've done is simplified this even more. Just said, lump all this sand into one unit, and I'm just going to block it off as a unit of clay and bury it uniformly. And what we see is that you get fluid moving up and out like that, and up and out like that, and it's really hard. The fluid flow in and out is pretty happy, and it's pretty hard to get enough pressure with squeezing and heating to generate any type of failure in that system. But if we change the geometry just a little bit, we keep that same sand layer down here, but I add a big pile of sediment on one side and a small pile of sediment on the other side. I've squeezed really hard over here. I haven't squeezed too hard over there, and it's easier for the water to flow from here to here and out than it is to go up through all of this clay. So here it has to go through 700 meters of clay. Here it has to go through a bunch of sand. That's really, really easy, and then only about 200 meters of clay. So what the water wants to do is it gets a bunch of energy added over here. It wants to go over there and go out. If it can't get out fast enough, it's my beer can experiment. The pressure gets built up over here, and I lift everything up, and it slides down the slope. And that's all we're trying to do. Is there a system that can do that? And being a simple-minded person, I said, well, can we simplify this even more? And this is the problem that we're solving. If anyone's ever played with the blob, I don't know if you have, but here's our aquifer. That's the blob right there. We have a little bit of sediment over here, young little boy. We have a little bit of sediment over here. And we have a big boy jumping off over here and coming down here, adding a lot of energy to the system very, very quickly. What's the easiest thing for that energy to do when he lands? Right, it's going to transfer from this side over to that side and pop him off. If he were to slowly climb down a ladder and sit down there, what would happen? He'd just tumble. But if he jumps down like he's doing now, the other kid's going to fly. And so basically that's all we're trying to do with all that math. We're trying to say, how fast do we have to add energy to this side of the system to create a failure on that side of the system? And so we come back to our slightly more complicated model, and we're going to look at sedimentation rate. How fast am I adding sediment over here? How fast am I loading sediment over here? How much do those rocks want to deform as they're being deposited? How squishy are they? The more squishy they are, the more water that has to get out. And how easy or hard is it for fluids to move from one location to the other? So we go back to our core data and we make some more measurements. First thing we do is we look at how fast the sediments are being deposited. And we do that by looking at the fossils in the rocks, and we can get ages at different depth horizons. And what we see, this is an age profile here from 65,000 years before present up to today. And this is how fast the sediments are being deposited. We see rates about 28,000 years ago at 10 millimeters per year. But at 50,000 years ago, sediment was coming in really, really, really quick, 30 millimeters per year or higher. That may not sound like a big number to you, but from an ocean drilling perspective or a deep ocean perspective, a half a millimeter per year is considered a high sedimentation rate. So we are significantly higher than that in this environment. On the east side, we have a different sedimentation rate profile. About 20,000 years ago, we have a high sedimentation rate comparable to what we have on the west. But then we have this long period where we're not getting very, very fast deposition rates over here. And then early in time, we're actually getting very high sedimentation rates on the east and not as high on the west. So we know basically how quickly that geometry created itself. So we have one piece of the puzzle. How quickly did we grow our sediments? Then we take a bunch of cores back to the lab and we measure how easy it is or hard it is to squeeze them and how easy or hard it is to flow water through them. So I'll show you some of those examples. We do that with a very simple vise. We take a sediment sample, about 5 centimeters in diameter, 2 centimeters in height. It's about the size of a hockey puck. For those of you who are giving up a hockey playoff game to be here, I appreciate that. We put it in this ring right here, and we apply a vertical force, and our sediment starts out at a certain height, and we squeeze it down to a new height, measure how hard we have to push to change its shape, or how compressible it is. Think about squeezing and stretching a spring. And while we do that, water has to get out, and we get a measurement of how easy or hard it is to do that. So we did that on a lot of core samples. And what we're trying to capture here, just to give everyone a mindset, here's the porosity. So 80% porosity means that the rock has 80% water, 20% solid grains. 30% porosity means that it has 30% water, 70% solid grains. And if we just look at one of those sites, the rocks start out with 80% water. By 100 meters below seafloor, they've squeezed out that water down to about 45%, and then that slows down with depth. And by the bottom of the hole, they have about 35% water. So what we're trying to do is we're trying to capture how those pores change shape and how stiff or squishy the rocks are at different depths. And we do that by thinking about how the squishiness changes with how much pore volume there is, schematically shown here. So a big McDonald's sort of straw here, a thicker walled straw, harder to, more solid, less open space, all the way down to something that's got a very, very small hole and more solid space. And we get a constraint at how the squishiness changes as the rock gets buried down deeper and deeper. And that's something that we need to know in our model, how hard it is to squeeze these things up here versus how hard it is to squeeze things down there, because that tells us how much fluid may be moving around in the system. At the same time, we get measurements of how easy or hard it is to flow in these different systems, and we get it for different lithologies. So we show some of the mud here, and we show some of the silt, slightly coarser grain size, and we get a relationship between, again, the pore volume, how big the pore space is, or how small the pore space is, and how either easy to flow it is up here, or as we squeeze those down farther and farther and farther, it gets harder and harder to flow. And we can use that straw problem again. When I have a big fat McDonald's straw, I can suck my milkshake out really, really easily. But then if I take a cocktail straw with a really, really small hole down there and I try to suck that milkshake out, it gets really, really hard because I've got a smaller area to move that through. So we come up with a relationship between pore space and ease or resistance to flow, and then we jumble all that stuff back into our computer model and try and solve how much pressure we generate. And I'll show you schematically what the model looks like. We start out with a horizontal clay layer at the bottom. We then add these white units, which are our sands. Then we add one of these first canyons that comes in and cuts. We add this second canyon that comes in and cuts. Then we add the mud on top of it, and then we add the mud on top of it. So this is 65,000 years ago, 60,000 years ago, 50,000 years ago, and present day. So we start out with a horizontal system, and we grow that wedge geometry over 65,000 years, and we just track how the pressure changes with time. And in the end, we get a picture of the pressure in the modern day environment, and we overlay our sites on it. So here's site 1324, and here's site 1322, and we get predictions of how much overpressure there is, or pressure above what we would expect when we dive into the swimming pool. Red colors mean there's a lot of overpressure. White colors mean that there's no overpressure at all, just like jumping into the swimming pool. And we see, just in our simple blob experiment where we added a lot of material overall relatively rapidly, we generated a lot of pressure. Where we added less material over the same time frame, or at a lower rate, we have less pressure. And fluids flow from high pressure to low pressure, and that's what those arrows are showing, is that fluids are migrating from left to right, adding more pressure over here than these rocks want to handle, and they're actually draining some of the pressure over there. I spend a lot of time in front of the computer making a model, and all models are wrong until they're tested. So the next thing we had to do is we had to say, well, does any of this have any basis in reality? So we went out on the drilling ship, and we took this probe down here. It's about the size of a pencil, and we lowered it down the drill string. So now we're lowering something the size of a pencil down the drill string through a kilometer of water, down another 600 meters below the seafloor, and we're sticking it into the ocean, and we're taking a measurement of the pressure. It's a really, really fancy tire gauge that you stick onto the side of your tire, and it pops out and tells you what the pressure is in the system. And we deployed that about 70 times in 2 different sites to get measurements of the pressure, and then we compare them to the pressures that we predict at this site and this site to see how well we're doing with our predictions. And at 1324, from the seafloor right here down to about 200 meters below seafloor, our yellow line, or our model predictions, is very close to what we measured in the formation. Deeper than about 200 meters below the seafloor, we consistently over-predict the pressure than is measured, and sort of beyond the scope of what we can talk about today, but if anybody wants to talk about it after the class, after the lecture, I'll be willing to go into why we think that that's happening. But we're going to focus on the upper 200 meters because that's where all the landslides are. Site 1322, which only goes down to 250 meters below seafloor, we see that our model prediction in yellow is very, very good match with the in situ pore pressure predictions. So we have to make a bit of a leap of faith here. We'll say that our model does a pretty good job of predicting the pressures today in an evolutionary fashion over 65,000 years to present. So we're going to say that we also could back calculate out what our pressures were in the past at the times of those landslides. And then we can calculate the stability. So we can go back to our beer can, and we're going to look at the stability of this system, which is just, we call it something called the factor of safety. The factor of safety is greater than 1, the system is safe. It's not going to fail. If the value decreases below 1, it's going to fail. And we input into that model the forces that resist failure, and that's just the frictional resistance to failure at the bottom. But that's controlled by the pressure, as we showed before. As I increase the pressure, there's less frictional resistance here, so it's more likely to slide. So we have frictional strength properties. Remember, I showed you some strength measurements earlier. That's the friction, and we're predicting what the pressure is. And then it's just comparing it to the driving forces, how hard gravity is pulling this system down and what the angle is that it's trying to slide down. And our angle in this case is about 1.5 degrees, the average background slope. And so what we did is we looked at our predictions at two different surfaces. We said, what was the factor of safety at different periods of time along this horizon, which was the seafloor 61,000 years ago. So we start over here at 61,000 years ago, and we start depositing sediments on top of it. And we just go through time from 61,000 years to present as we build this geometry at the site. So we're growing that wedge with time. And we say, for the given pressure, the given strength parameters, are we likely to have failure? And what we see is along this horizon, on the very, very eastern edge over here, we get factors of safety that are less than 1. The sediments are failing as they're being deposited. We're generating very, very small scale landslides as the sediments are being deposited. It deposits, it fails. It deposits, it fails. But then as this system gets thicker and thicker with time, there's more gravity pushing down, there's more frictional resistance, and our factors of safety across the entire model get very, very high, values above 12. We have a spike of sedimentation rate about 20,000 years ago, and the factors of safety decrease, but we never get failure again along this deep surface. But empirically, we had a bunch of failures that were really, really thin down here over at 1322, and our model predicted that we had failures there. So maybe at the first order, we understand how we can generate some of those failures. And now we're going to look at this 27,000-year surface, which is the base of those other slides, mainly the one with those blocky rotations in it, where we see actually discrete sedimentary blocks. And when we do the analysis on that 27,000-year surface, originally, it's very, very stable. Sedimentation rates, those are the blue and red lines here, are relatively low. Both sedimentation rates peak, so we're now adding more energy to the system more rapidly. So we're increasing the pressure fast, but our factors of safety only drop down to a value of about 3, and we don't get any failure. And then as the sedimentation rate slows down, we're not adding as much energy to the system, our stability numbers start to increase again. So in this region where we know we have large-scale failures that are very blocky, our pressure alone cannot drive failure. So we started scratching our head, asking what could be controlling the difference between these failures and these failures up here. And we said, well, let's look at our traditional stability model and add earthquake shaking to the system. So we're going to do the same analysis with resisting forces. Our pressure we already know. It's the same as the last example. Our friction we already know. We know gravity. We know the angle. And what we're going to do is we're going to predict how big of an earthquake, how much shaking do we have to add to that plate to get those failures to start moving down the slope. And without going into all the details, this is a summary of what's going on. So this is 100 kilometers for scale. Here's the Bird's Foot Delta of the Mississippi River, and all the black here is the Gulf of Mexico. And our study region, the Ursa region, is located right here in about 1 kilometer of water. And what we predict is for that failure on that 27,000-year surface, if we have a magnitude 4 earthquake inside this green circle at about 27,000 years ago, we had enough earthquake shaking to drive failure there. At the same time period, if we had a magnitude 5 earthquake about 100, 125 kilometers away or closer, we can generate failure on that same surface. If we have a magnitude 5 earthquake 20,000 years ago, it has to be a lot closer to the Ursa region because now we've got to move, we've got to mobilize more mass, so the energy has to be closer to the location of the failure. So we had a prediction of what type of earthquake might be required to generate this type of failure. And at this point, my graduate student asked if I had him running down sort of a dead-end path. He goes, we're studying the Gulf of Mexico. There are no earthquakes in the Gulf of Mexico. It's not the west coast of the United States. It's not the Ring of Fire. So we started looking at the earthquake catalog for the Gulf of Mexico. And that's each one of these dots here. These blue dots are magnitude 3 earthquakes. These 2 green dots right here are magnitude 4 earthquakes. And these 2 red dots are magnitude 5 earthquakes. And these are just the earthquakes that have been recorded in the Gulf of Mexico over about the last 30 years. So in the last 30 years, we've had earthquakes of the right magnitude in about the right vicinity that could have generated this type of failure. So we said there's possibly the same type of tectonic activity, the same magnitude of earthquakes that happened somewhere between 20,000 years ago and 27,000 years ago that could have destabilized that secondary failure at 27,000 years ago. So we sort of summarized this portion of the work where in that shallow section where we have that blocky rotation, again, you can see all those fault blocks rotating. You can sort of picture that in your head, that this surface right here that goes like that used to be a nice smoother surface like that, or even a smooth surface like that one up there, where we actually see relatively intact blocks. It starts out with moderate overpressure. It doesn't have a significant amount of overpressure, but it's got some. And when we look at this in more detail, the reason that this feature stays here is because it didn't move very far. We think these maybe moved on the order of maybe a few hundred meters at most. If we go down to this deeper section that looked like it was failing as it was deposited, we can see runout in the data on this of hundreds of kilometers, so orders of magnitude farther than the runout here, and that's why we lose all of the structure. And the difference here is that we have much higher initial pressure conditions. We get these much thinner, more chaotic failures, and we get much longer runout. So we said, well, we have some great data. We've put together a numerical story. We've collected as much data as we can with ocean drilling, and we had a good story, and we've been talking about this for a while, and now we've started to push this and say, what else can we do to do it? And so we've started to go to the lab. You guys have a great tsunami wave tank up the coast a little bit in Corvallis, and we've been playing in the sandbox too. We don't get to see these things in nature, so we're going to make them in the lab and see what we can determine. So we've been working in flumes trying to generate submarine landslides under different conditions. So now we're looking at much different scales. Here's 20 centimeters for scale. Built a low factor of safety environment, and by low I mean less than 1, so it's at failure, but a much, much lower than 1, so sort of maybe a 0.2 or something like that, where we have a lot of fluid pressure in the system. And this is the source area where the failure starts. And we see that when the factor of safety goes very, very low, we get this big cloud. It's a dense debris flow. You can think about this as an avalanche coming down the slope. It's got lots of fluid in it. It's buoyant, but it's moving relatively quickly down the slope. And it moves relatively quickly. Over 20 seconds, it moves a few meters, and it continues to go out farther. So we say, well, yeah, low factors of safety. You generate these very turbulent, very aggressive flows that can go out relatively far distances for their size. If we make a factor of safety closer to 1 and we generate failure, here's a different scale bar. Here's 10 centimeters for scale. We see that we get these very blocky type failure deposits that only move maybe 20 or 30 centimeters, so a couple orders of magnitude smaller than the movements here, and they show these very discrete fracture patterns and block deposits similar to what we saw in this example. This one had a moderate factor of safety, and then it took a little bit of a push from the earthquake to go, and we see blocks. This one had lots of overpressure, and it went on its own and ran out very, very far. So we had some more empirical evidence that we were getting closer to understanding the system, but we're not quite happy yet. So we've been continuing to do this with dynamic experiments. So here's a flume that we've been running some other experiments in. This is much more like a real system. We have a river coming in from the west. This is 5 centimeters by 10 centimeters. River coming in, sediments going across the plain and being deposited out. This is the water surface right here. And we're depositing sediments out on this surface right here. And it starts out relatively quiescently. We're generating these very, very thin flows as sediments go off sort of a cliff, if you will. They get deposited down on this slope, but they're relatively stable in the initial environment. And as we build up more and more sediments, you'll start to see that we start to get more and more mobilization, but we're not getting large-scale failures, but we continue to add mass to the system, and then at about this point, we've generated enough pressure in the system that we get something that runs out much longer. It's a destabilized system, and so now we're looking at this type of system to actually try to make dynamic measurements of how fluid pressures and landslide runouts are co-evolving, because we can't always measure everything in nature that we like, and you actually see there's another smaller scale failure up here. So where are we today? We're sort of pushing the frontiers, research opportunities, understanding. One thing, I mean, there's still lots of questions. We've talked about this earlier today in some of the groups that we were working in. All great science problems, answer 1 or 2 questions and ask about 10 more questions. You think about that as job security if you're a scientist. And so the things that we're looking at right now is how efficient is seismic shaking in soft sediments. I talked about a model today where we added earthquake accelerations, but we don't actually know how different sediments respond to those types of shaking. So we're going back to the flumes and we're adding earthquake accelerations. We've talked about a couple ways to do that, but the coolest way that we've come up right now is to put a bunch of subwoofers next to the tank and play some big bass music that goes boom, 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 starts shaking the system and measuring how that generates different types of landslides. We're instrumenting that flume with pressure transducers so we can actually get more validation to our model prediction. And then what we can do is we can change the pressure response by how quickly or slowly we add sediments. We can change the shaking, and we can get back to sort of this question of what are really the controls on the size and shape of failure. We have some good observations, but we don't really have the best answer to that. And then the last thing would be starting to work with the people who are doing tsunami models to actually couple, as these sediments start moving down the slope and disaggregating, how that perturbs the ocean surface. There are people that do ocean surface tsunami modeling for blocks that slide under the ocean, but they don't actually do it with deforming substrates. And you just saw in that last example that the material that's moving is disturbing and deforming with time. So those are some of the questions we're tackling today. But in summary, what we've covered now is really, really large-scale slope failures on low-angle slopes. So things that move up to hundreds of kilometers on slopes, again, think about this, at 1 degree, something like my arm out here, it definitely requires weakening by overpressure. We have a pretty good control on how to generate that overpressure. It's a competition between how fast the system's growing and how quickly the fluid pressure can be dissipated by fluid flow. We can trigger some landslides, but there's very few of them that we can trigger by overpressure alone. So oftentimes we have to look at other mechanisms like earthquakes. So that Sahara Slide and Sahara Slide that I showed you at the beginning have both also been tied to small magnitude earthquakes, sort of magnitude 4, magnitude 5, and a modest amount of overpressure at the time of failure. And the thing that we're tackling right now is the trigger mechanism, whether it's overpressure alone or overpressure followed by earthquakes, is what possibly we believe is generating the failure type. Is it thin? Is it chaotic? Is it blocky? And its runout length. Does it move hundreds of meters or hundreds of kilometers? And when you add all that up together, that is the tsunami potential. And that's where we're going with this line of research. And now I'll take any questions that people have. Thank you very much.
Thanks, Brandon. As we go into the questions, thanks to Floyd and Dean and Dallas for all year providing the live stream as well as archiving things.
One question is basically, I didn't see in here, is about the size and the shape of the particulates in there, that it's much easier to slide on clay sediment than it would be, let's say, sandpaper, or sand kind of, because of the texture. Right. And shape and size.
Right. So there's a component that's hidden in here if you think about the can sliding, that's the frictional resistance. So the interesting thing here is all the slides that I talked about in detail, all the material is homogeneous clay. So it's relatively easy to slide down, and that's part of the reason is clay is a weak material, so that allows some of the sliding. Clay also allows a lot of pressure buildup, so that's also what we see. So what we see is if we go to very, very sandy environments, we don't see as many large failures. One, because the frictional behavior is different. It's actually frictionally a little bit stronger. But two, it's much harder to generate pressure because it's easier for water to flow out of sand. So as I load it quickly, the water goes out quickly, and I never generate this excess pressure. It never gets trapped in there. So it's kind of a leaky water balloon. As I squeeze it, the water just goes out, and I never burst it. So yeah, those rock properties are not just not just controlling the flow, but also the strength of the materials as well.
Have any other questions? No, it's not about him. It's about.
You know, I see the research you've done and what it shows and as far as the effects of what's going on. But I'm curious as far as what it might shed light on as far as ecological impacts or geological situations past or present that we could learn from it beyond what you shared.
I guess from the ecological impacts or geological impacts, what a lot of people are looking at right now is anytime you look at a coastal environment, if you have a tsunami, you are going to flush a bunch of salt water up onto that system. And we've seen this after Banda Aceh in 2004, in Tohoku in 2011. If you flush a lot of fresh water up, or a lot of seawater up on the land, all your freshwater environment is going to be catastrophically inundated. It's going to die. It's going to struggle. In India, where they have large coastal populations after Banda Aceh, they had a huge problem with freshwater resources because they have a lot of coastal aquifers that they're extracting drinking water out of. All of those aquifers got overrun with salt water, so they no longer had the volumes of drinking water that they had in that time. So what we can do with this type of analysis is we can't exactly predict when a landslide is going to happen, just like they can't predict exactly where an earthquake is going to happen, but we can make sort of quick calculations of where the most likely locations and the most risk-prone environments are, so people have a better idea of whether they should be prepared for something like this or not. And that goes everything from insurance vendors who've called me and said, do I need to raise my insurance investments on this coast, to people who are looking at building beach barriers to prevent waves from washing up onto land. So we can make predictions or risk assessments, I guess is probably a better way to do that. Does that answer sort of your question?
At what risk are we when you consider all the oil fracking that's going on off the coast for submarine landslides?
So fracking is a similar type of process in that we're relating rock strength to fluid pressures, and what they're doing is they're increasing the fluid pressures and generating a fracture, which many of you have realized generates small earthquakes, or where they're re-injecting fluids generates larger earthquakes. So far, we think that there's probably a disconnect between the landslide issue and the fracking issue, just based on the scale of the problem. So the landslide problem, we're looking at things that extend over tens of kilometers at the failure surface. Fracking jobs are, kilometers long, type things like that. So it's a much smaller scale. Also, the amount of energy put into that system is much different. So there are coastal examples of natural hydraulic fractures that are hundreds of meters to kilometers long that we think are related to similar processes like submarine landslides. And they require amounts of energy and fluid that are significantly larger than fracking. Fracking does have risks associated with contamination and earthquakes from reinjection, but in terms of triggering a submarine landslide or adding enough pressure to increase the risk, it's probably not much of a risk. It's a separate set of problems on its own.
One more question.
Do you see evidence of this phenomenon on shore in areas that had been submerged in previous ages?
This was actually, so one of the first, the way that problem worked is when people started studying submarine landslides, they took all the onshore information that they had and they tried to apply it to the offshore environment. And we don't see these types of failures in onshore environments. We don't see failures at much low-angle slopes. The physics of the problem are loosely the same. So if you go to California in an El Nino year, what you see are lots and lots of mudslides. And what's happening there is all the rainfall is raising the water table, and that's just raising the water pressure, and that's facilitating some of these failures. And other people have looked at, in stable environments in coastal California, actually, how big of an earthquake will generate a landslide. So we're taking the similar types of approaches, but what we see in the submarine environment, which is different, is the landslides are all significantly larger. We're talking, 10 times larger and they're failing on much, much lower angle slopes. If you go to coastal California, it's 30-degree slopes. They're almost at their failure angle, and then a rainstorm comes in or a small earthquake comes in and everything catastrophically releases. And part of that is the effect of the fluids that you're failing in. So on land, you're failing in air, and in the ocean, you're failing below water. And so there's a different force balance there, but at a very, very loose area, the problems are the same, but they're happening at very different angles and under very different time scales.
So I'd like to thank Brandon for making time in his schedule, Ocean Leadership for providing the sponsorship for bringing him to Coos Bay, as well as everybody else that's been here this weekend, and also for all of you for coming out throughout this year. It's the last talk in the series this year, but you can also pencil Friday, October 11th on your calendar. The Geology Lecture Series and OIMB Public Lecture is going to host Deborah Kelly from University of Washington talking about hydrothermal vents, and I've been told that she has to also bring some information about biology for OIMB as well. So there hopefully will be 6 talks next year, but we've already got one penciled in. So thank you all for coming out this year and this evening, and see you next fall. And as Brandon said, I'm sure he'd be more than happy to stick around and answer some additional questions from you as well.